Today begins our discussions of polynomial functions. And what is a polynomial function? That's anytime you have an x and then you have some sort of exponent with a number in it. So it could be something like x squared, x cubed, x to the 10th, etc. Maybe with some other x's to other powers added on. These kind of spicier polynomials we're going to go over later. That's going to be about next lesson. But today we're really going to focus on ones that take the form x squared, or maybe x squared being multiplied by something with a few other lower powered things being added. Either of these sort of taking the form of a quadratic. And that's really going to be our focus of today, is diving deep into what do these quadratic functions look like. This may be the type of polynomial you are most familiar with, or it might be brand new. Either way is completely fine. But we're going to be going over today all the different ways we can think about quadratic functions, all the different uses for them, and really understanding these deeply. As always, feel free to jump to a particular timestamp in this video if there is a particular type of problem that you're wanting to know about. First, kind of most basic way to think about how do I write a quadratic function is to really think of it as a transformation. And that's all this fancy word of vertex form means. So first of all, what is a vertex? Well, the vertex is this highest or lowest point on the quadratic. It's the only one where there's a single x value that gives you a single y value. In this case, the point 0, 0. And everything else builds symmetrically from there. For example, and this is the function just y equals x squared, or in function notation, f of x is x squared. So when I plug in 0, f of 0 is equal to 0 squared, which is 0, which I can put on a nice beautiful table. So I could think of 0, 0 here in the center as my vertex. And everyone else is going to build around him. For example, plugging in either negative 1 or 1. Well, if I do negative 1 squared, that's positive 1. If I do positive 1 squared, that's also positive 1. So that builds symmetrically around the point 0, 0. And I could think of other points as well. I could even jump over here to 3. So when I plug in positive 3, well, 3 squared gives me 9. And similarly, if I plug in negative 3 squared also gives me 9. So there's this really beautiful symmetry that happens around this quadratic function. The word that we had learned for that earlier was that it's even. It's the most quintessential even function. Whenever he's in kind of this basic form, if we transform him, he may not be even anymore, all depending. But at least this way, he is even. And that if I fold him over this y-axis, he still has this nice, beautiful symmetry to him. We can think of how maybe this thing can get transformed, though. So if we look at this new function, how does he appear to be transformed from the original? Well, this vertex in particular moved right 2. And how do we write the transformation moving right 2 again? Well, we stick that inside the parentheses with the function, and we use the opposite sign. So to move right 2, that would be x minus 2. And that would be my new function. Now we really want to also check if he's been stretched or reflected or something like that. So if we notice in particular, the other points have the same relative relationship to the vertex on this one as it does on the original. In particular, for the next points, I went up 1 over 1, up 1 over 1. Then for 2, that should be over 2, up 4, over 2, up 4, over 2, up 4. So I could just notice that from the graph, or there is a way I could formally check. So I could say, I know that the vertex moved right 2, but maybe I can't check by hand, or I'm not confident of checking if he's been stretched. Put in a little placeholder, call him A, because that's what we called him back when we learned about transformations, and then plug in a point that's not the vertex to solve for that. So in particular, it looks like this y-axis, this y-intercept of 0, 4 might be a nice point to plug in. So it should be the case that when I plug in 4 for y, keep a placeholder for the stretch, and plug in 0 for x, I can solve for if there's a stretch factor. 0 minus 2 gets me negative 2. All squared gives me 4. So I'm left with 4 is equal to a times 4. And then as my last step to get a by itself, I would divide by 4 on both sides. And lo and behold, my stretch factor is just 1, which is nice. It's not one that's necessary to write, although you can if you want. So my entire equation is f of x is equal to x minus 2 all squared. And this is something that even without me telling you a formal vertex form, you could hopefully figure out from your knowledge of transformations. That as long as you knew that this was f of x is x squared, which before I would have told you, but now I would expect you to sort of recognize that this U shape that's symmetric is the equation f of x is x squared. Once you know that's f of x is x squared, you see where has that vertex moved. You do any left-right shifts and up and down shifts according to where that vertex has moved. And then you check, did this guy also stretch? You can either kind of check that by knowing how some basic points on the vertex on the graph should look relative to the vertex, or you could actually just plug in a point. Oftentimes the y-intercept is the nicest point to plug in and solve for a potential stretch factor. There's a little bit of vocabulary that we tend to use when talking about quadratic equations. So where it's symmetric over is known as the axis of symmetry. So on a basic quadratic equation, it is literally symmetric over the y-axis, which is what makes him even. But every single quadratic, even if I move him around, will have some type of axis of symmetry. So in this case, the axis of symmetry is the line x equals 1, because I could fold the quadratic over the line x equals 1. The vertex is always this highest or lowest point. It's something we're really interested in. And that tells us by itself exactly where the left and right shifts are on this new form of the quadratic. So in this case in particular, the vertex is at the point right 1, down 4. So we have 1, negative 4. So I already know this equation somehow looks like x minus 1 all squared, opposite sign there, and then a minus 4 on the outside for that up and down shift. And the only thing I don't know is, was this guy stretched? And then I could plug in one of these points to figure it out. I could plug in perhaps the x-intercepts. So we have an x-intercept here at 3, 0, where it physically crosses the x-axis. We have an x-intercept at negative 1, 0, where it physically crosses the x-axis. Or I could plug in maybe a y-intercept, where it physically crosses the axis down here at 0, negative 3. Or I could plug in literally some other random points. So that could be, for example, this point here at 4, 5. That could be another random point. And just to really emphasize, let's show what plugging in that random point to solve for the stretch factor would look like. I would plug in 5 for y, because that's a random point that I know exists on the graph. Keep that unknown stretch factor, because that's what I want to know. Plug in 4 for x, drop down that minus 4, and then I start to evaluate this with order of operations, with the goal being to solve for the stretch factor a. So in particular, I'm going to simplify inside the parentheses first. 4 minus 1 gives us 3, all squared, and then we have this minus 4 over here. 3 all squared gives us 9, so we have a times 9 minus 4. First thing we want to undo is any addition subtraction, so I want to add 4 to both sides. We get 9 is equal to a times 9. Then I want to get rid of multiplying by 9 by dividing by 9. 9 divided by 9 gives us 1. So I just figured out that stretch factor is 1. So I could write the times 1 if I wanted to, like this. That's not technically wrong, but a lot of times we don't actually write when we're multiplying by 1, because multiplying by 1 doesn't really do anything. It's the identity multiplication function. And that would be my final equation for this. Sometimes there is a stretch factor though. So in particular, this stretch factor out here, because he's negative, we already know this guy should be upside down, because whenever I multiply a negative out front of anything, that reflects that over the x-axis. It is a vertical reflection. So as soon as this multiplication factor out front, as soon as the stretch factor is negative, that leading number, if you will, as soon as that's negative, I know this guy is upside down. And then he's also being stretched further by that 3. So how could you have come up with this equation without me telling you it? Well, let's go through that. So here, in particular, we can notice where the vertex is. So the vertex moved left 2 and up 4. So that already tells you most of what you need to know. So I can have an unknown stretch factor. And to move left 2, I need to do opposite signs, so minus and negative 2 becomes adding 2, all squared because we're dealing with a quadratic here. And then up 4, I keep the same sign there to deal with that up and down shift. Then if I wanted to solve for this stretch factor, I can pick any sort of point on the graph. Here it looks like they've already pointed out to us that we have the point -1, 1 in particular. So I can plug in +1 for y, -1 for x, and then keep everything else the same. Now I follow order of operations, so I want to simplify inside the parentheses first. -1 plus 2 gives me 1. 1 squared is just 1. A times 1 is just a. And then as a final step, I need to undo adding 4 by subtracting 4 on both sides, and I get a is equal to -3. So that tells me that my final equation is exactly the same thing that they noted, of -3 parentheses x plus 2 all squared plus 4. And that form that is really just your knowledge of transformations is what's known as the vertex form of a quadratic function. And it is oftentimes, anytime you're given a quadratic function, let's say his graph or just information about him, like this is the vertex and this is another random point, this is the nicest form to work with. And whenever you're working with this form, you want to look at where has the vertex shifted, and that is h comma k. So if I told you that previous equation of -3, what was that? X plus 2 all squared plus 4, you could already tell the vertex was here, of opposite sign on the 2 for a -2 and same sign on the 4 for a +4. That's why they have the -h noted, because it's always the opposite sign on the x coordinate of the vertex in there. Same sign on the y coordinate for the vertex, and that's again tying into transformations. Then you can plug in another known point for x and y, and then you can solve for the stretch factor a. And this is actually a technique we're going to use very often in this section, where we plug in our known information and another point, and then we solve for the potential stretch factor. Since really the best way to solve for an unknown stretch factor is to plug in what you know, and then hopefully the stretch factor is the only variable left. You solve for them, and then you can just write your generic equation. So let's practice that a little bit. I want to challenge you to go ahead and pause your video and try to write the equation of this first one on your own before comparing with what we get. So for this one in particular, I want to definitely note my vertex, which is at the point 3, 1. And then I want to note a different point on the graph. When I can plug in the y-intercept, that's typically a really nice point to plug in, which in this case is at 0, 7. So I can plug into the generic form that I have y equals a x minus 3 all squared plus 1, because I do opposite sign on the left-right shift, same sign on the up and down shift. Then I can plug in my other points. So when y is 7, x is 0. Then I start to follow order of operations. So I want to evaluate inside the parentheses first. Well, 0 minus 3 gets me -3. All squared gives me 9. Then I want to undo any addition subtraction. So 6 is equal to a times 9. Then I want to undo multiplication division, so I can divide by 9. So a is equal to 6/9, which is equivalent to, both of these can be divided by 3. 6 divided by 3 gives us 2. 9 divided by 3 gives me 3. So our final equation is y is equal to 2/3 parentheses x minus 3 all squared plus 1. And that was just taking this form and replugging in a. As a sanity check, if it's an upward-facing parabola like this, you should not have any sort of reflection going on with that a, so that a should be positive if that is the case. Go ahead and pause your video and see if you can write the next quadratic equation yourself. So hopefully the first thing you noticed was that the new vertex is at -2, -3, which already tells you a lot about the equation, because you know it'll be in some sort of format of some sort of multiplication factor, x, and then we want to use opposite signs, so this time +2, all squared, and then we are moving down -3. Then you want to pick some point in order to figure out, does he have some sort of multiplication factor? So in particular, I noticed that the y-intercept might be nice at 0, -1. So I plug in -1 for y, keep my multiplication factor, plug in 0 for x, and then I can go ahead and start solving. So first thing I want to do is simplify these parentheses. 0 plus 2 gets me 2, all squared gets me 4. So then we have a times 4 and a minus 3. And then I want to undo any addition and subtraction, so we undo -3 by adding 3. -3 plus 3 makes 0, -1 plus 3 makes 2. And as a final step, we again want to get a by itself, so we are dividing by 4 to undo multiplying a by 4. So a is equal to 2/4. 2/4 is a fraction that does simplify because I can divide both the top and the bottom by 2 to get us a half. So our final answer, plugging in that we know a is equal to a half, is y is equal to 1/2, parentheses x plus 2, all squared minus 3. And that would be our final beautiful quadratic equation. We could also move the other way around, where we want to plot the quadratic equation using a series of transformations. So in particular, in this first one, the first transformation that happens is inside these parentheses. This transformation moves him to the right 1. Then this negative on the outside reflects him over which axis? Over the x-axis. Vertical reflection. So let's actually move this quadratic equation in that way. So that means our new vertex, instead of being at 0, 0, we'll move right 1, which moves him to +1, 0, and then will be reflected over the x-axis. Well, that doesn't do anything when the y value is 0. Then we can put another couple of points on the original quadratic equation, and it might make sense to kind of to the side keep note of that. So on the original quadratic equation x squared, we have the point 0, 0. We also have the point 1, 1, because when we plug in 1 for x, 1 squared gives us 1, and we have the point -1, -1. For now, we're just going to stick with those 3 points, but if you had to make 5 points, you would also want to maybe trace where the point 2, 4 moves, because normally when I plug in 2, 2 squared gives us 4, or where the point -2, 4 moves, because normally when I plug in -2, that also gets us 4. So let's move those other points. So in particular, let's maybe move 1, 1 and -1, 1. So we have 1, 1. Want to think about where that moves. Well, when we move him right 1, 1 moved right 1 makes 2. So initially at 2, 1. But then we want to reflect him over the x-axis. So his final place, which I'm just going to erase over to right, would be at 2, -1, because reflecting over the x-axis flips the sign on that y value. So we also have a point at 2, -1. And quadratic functions are symmetric, so just as equally far away, I have the point here at 0, -1. That would have come from moving the point -1, 1, which you can confirm for yourself if you don't believe me that is symmetric, or just as a good exercise. Then we can think maybe about where the point 2, 4 is going to move. So to move to right 1, that moves him to 3. And then we are going to end up reflecting over the x-axis, so that changes the sign on the 4 to be -4. So we have a point at 3, -4. And just as far away from the vertex, to keep this guy symmetric, that would be an additional point there. And now you have made your nice, beautiful quadratic equation actually through 5 points, which we were able to think about by just thinking about where 3 points were and knowing that he is symmetric. Let's do a similar thought process for this next one. So let's think about all the different things that happen here. So the first transformation that happens is inside this parentheses, we're moving left 1. The second transformation that happens, which I'm going to do in another color, would happen from this 2 being multiplied on the outside. That would stretch our quadratic equation by multiplying the y values by 2. Then the last transformation comes from this -2 on the outside, which would shift everything down 2. And we are going to go ahead and predict, even regardless of this multiplication factor, that we expect the vertex to still be at the point -1, -2, because we want to move left 1 here and down 2 here. So let's actually do all those different transformations in order. And let's kind of keep track of the points that we are transforming. So we're transforming the point 0, 0, we're transforming the point 1, 1, and we're transforming the point 2, 4. So for the very first transformation, to move these guys left 1, that moves 0, 0. Left 1 moves 0 to -1, 0. It moves 1, 1. Moves the positive 1 left 1 to 0, 1. For 2, 4, to move him left 1, that moves the 2 to 1, 4. Then we want to multiply those y values by 2. And already I can tell that maybe I want to give myself a little bit more room, but I'll continue down. It's okay. But I am going to zoom this in so that you can maybe see a little better. So now we want to multiply those y values by 2. Well, 0 multiplied by 2 is still just 0, so that hasn't moved further. For 0, 1, we multiply that by 2. That 1 moves to 2, because 1 times 2 is 2. And for 1, 4, to multiply that by 2, well, 4 times 2 is 8, so that moves to 1, 8. Then as the final transformation, we want to move all these points down 2. So -1, 0, 0 moved down 2 moves to -2, just as we predicted that vertex should be. For the next point, 0, 2, to move 2 down 2 moves to 0, because 2 minus 2 is 0. And for the last point, 1, 8, 8 moved down 2 is 6, because 8 minus 2 is 6. So we move to -1, -2 for one of the points, 0, 0 for another point, and we're going to utilize the fact this guy is symmetric. So we should have a symmetric point about the vertex over here. And then 1, 6 is the last point, and again we're going to utilize the fact that this guy is symmetric. So the last point would be over there. And that is about this axis of symmetry that exists through the vertex, if you want to better visualize that symmetry there. And that would be our final beautiful parabola. And if you don't like graphing parabolas from transformations, we're going to go over other methods as well. If you didn't like explicitly thinking in terms of transformations, you could also pick a couple of x values to just plug into the function. And then if I was going to do that, I would just make sure that you kept this vertex in the center and plugged in some that were a little bit bigger and some that were a little bit smaller. That would have been another way to confirm that this transformation would look this way. Another common way that you might be asked to think about quadratic equations is that you are given information about the quadratic and then you have to write the equation. So not necessarily given the graph, but given the information in some other way. So it says we have a quadratic function with a vertex at -4, 7 and a y-intercept of 9. So even though I can't see it visually, I already know I could have some multiplication factor, and then I'll have an x plus 4 all squared in parentheses to say that he's shifted to the left 4, and then we'll have a plus 7 here on the outside to say shifting up 7. Since they gave us that we have a y-intercept of 9, we really have the point 0, 9 that I can plug in. So I'm going to plug in y is 9, plug in x is 0, and now I'm good to solve for my unknown multiplication factor. Following order of operations, I want to deal with these parentheses first. 0 plus 4 gets us 4, all squared gets us 16. Then I want to get rid of adding 7 by subtracting 7 on both sides. So I get 2 equals a times 16. And then as a last step, I want to divide by 16 to undo multiplying by 16. And we end up with a is equal to 1/8. So our final quadratic equation with a plugged in is y is equal to 1/8 x plus 4 all squared plus 7. Go ahead and try the next one yourself and then compare with what we get. So we're going to set it up a similar way. We'll have an unknown multiplication factor and then say, okay, we're going to take away 8 to say that we're going to move right 8. all squared, and then subtract 10 on the outside to say moving down 10. Then we can plug in this point, so we plug in y is 6, x is -1. And then we can simplify from here with the goal to solve for the stretch factor. -1 minus 8 gets us -9. -9 all squared gets us 81. Then we want to undo subtracting 10 by adding 10 to both sides. So we get 16 is equal to a times 81. And then as a last step, I want to undo multiplying by 81 by dividing both sides by 81. Then I might want to ask myself, does 16 81ths simplify? Well, the only things that go into 81 are things like 9, 3, neither of which go into 16. So that's not super helpful. Because 81, right, breaks down into 9 times 9, which breaks down into 3 times 3, into 3 times 3, so different factors would be 9 times 9. We also could have 3 times 27. We could have 1 times 81, but none of those are things that go into 16. So this is just going to be a funky fraction, and that's okay. We'll have y equals 16 over 81 times x minus 8 all squared minus 10, and that would be our final beautiful answer. In general, we're allowed to plug in anything to a quadratic equation, and as long as we keep that multiplication factor positive, he's going to stay facing up with a minimum here at his vertex, which has the coordinates h, k, so the range will be from k to infinity. If that lean coefficient is negative, then he'll be facing down with a vertex still at h, k. So the domain would be from, and there is a typo here that should say from negative infinity to k. And that will be fixed on your version. So let's say you aren't given something in vertex form and you want to make him look like vertex form. Well, we can do that by completing the square. And what do we mean by that? We say that we want to figure out a way to make this still look like this equation, where you have an x minus h all squared, and then plus k, and in order to do that, at some point I need to have that thing of x minus h squared. So how do I make that happen? Well, I cheat a little bit, and I say I know how this will happen. If I have two parentheses such that they are repeated, whenever I factor out something, that's going to make that happen. So what trick do I do, so to speak, in order to make that happen? Well, that's going to happen if this last term is the middle term divided by 2 squared. That's the only way I would then ask myself what multiplies to this and adds to this, and this is the result. And so let's see that in action. So here, what would b be considered? It would be considered 4. So then we can say, okay, let's rearrange this to be x squared plus 4x plus 4 over 2 all squared minus 4 over 2 all squared, and then we still have the minus 7. Since we added and subtracted the same number, I haven't changed the value of the equation. I sort of expanded him out in uncombined like terms so that I can make something super nice happen. In particular, we want to note, of course, what 4 over 2 squared is. 4 over 2 gives us 2, all squared is 4. It's sort of unusual. It ends up being the actual literal number itself, but it worked out that way for now. Then we want to group this part together and say what's going to multiply to positive 4 and add to positive 4. Well, that would be positive 2 and positive 2. And since the leading coefficient in front of the x is 1, we can just jump straight to the parentheses. We may want to go ahead and combine these like terms as well. Negative 4 minus 7 gets us negative 11. You might be asking yourself, how do I know if to write plus or minus first? Well, if you wrote it the other way around, then when you go to the step, it no longer works, because you'd be asking yourself, what multiplies to negative 4 and adds to 4? And that very literally, like at least I cannot think of anything that would work for, and it certainly wouldn't be something that repeats. So you know you did it wrong if it just doesn't work, and then try flipping it the other way around. That's kind of the easiest place to make a mistake. Now I know that if I have x plus 2 times another x plus 2, a shorter way of writing that is x plus 2 all squared, and then I drop down the minus 11. So now I know that my vertex is at the point -2, -11, because I flip the sign on the left-right shift and I keep the sign on the up and down shift. Go ahead and pause your video and see if you can complete the square yourself for this example. First thing you want to do is identify what b is, in this case -10. So here I want to go ahead and expand out that we have x squared minus 10x plus -10 over 2 all squared minus -10 over 2 all squared plus 3. Then I want to note what that actually is. -10 over 2 gets us -5 all squared is plus 25. -10 over 2 is -5 all squared, again 25. So I've really just fancily added 25 and then subtracted it right away. Then here I want to start to factor, so what's going to multiply to positive 25 and add to -10? That would be x minus 5 and x minus 5, because -5 times -5 is positive 25 and adds to -10. Here, -25 plus 3 gets us -22. We can just combine those like terms. Now that I have an x minus 5 times an x minus 5, that can simplify to make x minus 5 all squared minus that 22. And so these are exactly the steps that you do to complete the square. Now, if there is a leading coefficient out front, you still can complete the square, but it's much more prone to error. Because in particular, when you do this step of adding and subtracting b over 2, you would have had to first factor out that leading term in order to make it work. And then whenever you pull this term out that's not being squared out again, you have to remember that this 2 distributes to him. So that in particular can be very prone to error, which is why, unless you're very, very comfortable with it, I don't recommend completing the square if there is a term in front of the x squared. You still can. This is how you do it if you do want to do it that way. I'm not going to spend a lot of time on it because I don't recommend it for these cases. We have other methods that I would much more strongly recommend instead. And that's exactly what we're going to jump into now. So if you're not given something in vertex form, but you still want to know about, well, where's the vertex? Where's the axis of symmetry? Let me find some intercepts. There are some other methods that you should be using. So in order to graph any sort of quadratic function, in general you want to find the vertex. You could kind of use transformations like we were doing before, but it's also going to be helpful maybe if you find the x-intercepts. If you find the y-intercept, which by extension, finding the y-intercept means that you have also found an equivalent point just as far away from the vertex as the y-intercept. And then if you have no x-intercepts, because not all quadratic functions do, still find at least one other point so that you're not just graphing only a vertex and a y-intercept. Then you can connect them to make your nice, beautiful parabola. In particular, if it's not given to you in vertex form, a way that you can figure out the vertex is this nice, beautiful equation. I've included a proof of why does this equation work for you, if that's the sort of thing that interests you. But the short of it is that you can find the x-coordinate of the vertex by doing -b over 2a. And that's always going to be your x-coordinate of the vertex. There are some places online that will give you like also a very complicated formula for the y-coordinate of the vertex. I don't recommend doing that. Just once you know the x-coordinate of the vertex, then you plug it in to find the y-coordinate. That is much more simpler and also shows that you actually understand what you're doing as well. And that's all this is saying, is that you want to actually plug in what you find to be the x-coordinate of the vertex to find the y-coordinate. And this is again just reminding you that once you have found that y-coordinate, missing some parentheses and a negative there, once you've found that y-coordinate, you know if it's concave up, if it's right side up because that a is positive, then that means that the domain is from that y-coordinate of the vertex all the way to infinity. If he's concave down because I reflected over the x-axis at some point, then you know that that range, sorry, if I said domain earlier, I meant range. You know that range is from the y-coordinate of the vertex to infinity. or you know that range is from the y-coordinate of the vertex to negative infinity. For the domain, that's always negative infinity to infinity. I can always plug in any x's to a quadratic function. So let's practice finding the vertex. So in particular, the x-coordinate of the vertex is negative b over 2a. So in this case, negative b would be negative 16 over 2 times 4 is a. Negative 16 over 2 times 4, well, 2 times 4 gets us 8. Negative 16 over 8 is negative 2. I'm only halfway there because I've only found the x-coordinate of the vertex. To find the y-coordinate of the vertex, I then plug in negative 2 into the function. Then I want to follow order of operations in order to simplify this. Negative 2 all squared gets us 4. 16 times negative 2 gets us negative 32. 4 times 4 is 16. 16 minus 32 is negative 16. Negative 16 minus 9 is negative 25. So our final vertex would be at negative 2, comma negative 25. Where does that mean the axis of symmetry is? That I actually could have answered first. That's just x equals the x-coordinate of the vertex. It's a straight up and down line through the x-coordinate of the vertex. What about the domain? That's just negative infinity to infinity always. And then what about the range? That's going to be from the y-coordinate of the vertex all the way to positive infinity because he's right side up. Go ahead and let me zoom this out a little bit. Go ahead and try the next one yourself and then compare with what we get. In particular, you might want to first find the x-coordinate of the vertex, so that's negative 18 over 2 times negative 2. 2 times negative 2, it gets us negative 4. Negative 18 over negative 4, a negative divided by a negative is a positive. And also 2 goes into both of these, so this simplifies to 9/2. So I've already figured out that the axis of symmetry is through x equals 9/2. Then I want to figure out the y-coordinate of the vertex, so in order to do that, I'm going to want to plug in 9/2 into this equation. And once I've shown this work, I would actually say these numbers are funky enough that I would break out a calculator. So we've got negative 2 times 9/2 all squared plus 18 times 9/2 minus 10. So that gets us 30.5, or as a fraction, 61.5. So we know that the vertex is on the point 9/2, comma 61.5, or 61/2 I should say, sorry. I was making that sound like a mixed number. 61/2, or 30.5 as we found out. What does that mean the domain is? Always negative infinity to infinity. What about the range? Here, since a is less than 0, that leading coefficient is negative. He must have been reflected over the x-axis. And we go from negative infinity to 61 over 2, inclusive. So this is an upside down parabola here. The other one was a right side up parabola. We know that from that leading term. We also still know how to find x and y intercepts, and this was actually a part of quadratics that I've been able to ask you since the first week of school, because we went over how to find whenever a quadratic is equal to 0, that's finding an x-intercept, and you also know how to plug in 0 to a quadratic in order to find the y-intercept. Keep in mind, it is possible there is no x-intercept, so you will get an imaginary number, which is something we'll be going over at the end of this unit. In short, if you ever are trying to do the quadratic formula and you have a square root of a negative, that's going to be no x-intercept. It's possible there's just literally one x-intercept, that's cool, or it's possible there's two. It's not physically possible for there to be more than that, though, and that's actually an idea that we'll be circling back to. But if you don't believe me on that, try to sketch it out, try to make a quadratic that has more than two x-intercepts. You hopefully should find that it's not physically possible. If you somehow find that it is, contact your professor. You have just made a new mathematical discovery and the fundamental theorem of algebra is broken. So congratulations. But most likely that won't happen. Most likely you should convince yourself of this rule. Does there need to be a y-intercept, though? Pause this video and ponder that question for a moment. There does, because since the domain is from negative infinity to infinity, we're always eventually going to cross the y-axis no matter what. So there will always be a y-intercept. Since he goes infinitely in both directions, he does eventually hit the y-intercept. So let's find some intercepts. So first thing we might want to do is I actually usually like to find the y-intercept first, because that usually boosts my confidence. Because when I'm finding the y-intercept, it's plugging in 0 for x. And what do you notice happens? That first term goes away and becomes 0. The second term goes away and becomes 0. I'm just left with the last term. So there's actually very minimal arithmetic needed to find the y-intercept, which is sort of nice. For the x-intercept, I plug in 0 for f of x instead, because I'm plugging in 0 for y, and f of x is another name for y. Then I want to think through what's the best method to solve this. So first of all, if all three of these terms have a greatest common factor, I definitely want to factor that out first. In this case, they don't, though, because of this pesky -9. Like 4 and 16, 4 goes into both, but for -9, only 3 and 9 and 1 go in, so that's not very helpful. Then I want to see if the AC method is going to work. So A times C, that's 4 times -9 is -36. So I want to see if there's anything that multiplies to -36 but adds to +16. So if I'm brainstorming some factors of -36 that will actually eventually work, as +18 and -2 will multiply to -36 and add to +16. Remember, when I do that, I can't jump straight to my parentheses. Instead, I'm breaking up that middle term. So I have 0 is equal to 4x squared plus 18x minus 2x, drop down the -9. Then I want to do my grouping. Between 4x squared and 18x, their greatest common factor is 2x. 4x squared divided by 2x leaves me with 2x. 18x divided by 2x leaves me with +9. Here, there is no greatest common factor, but if I kept it as is, I would almost match this parentheses, but the signs would just be flip-flopped. So that's a cue for me to pull out a -1, because then -2x divided by -1 gives me +2x. -9 divided by -1 gives me +9. And now I'm in business, because now I have 0 is equal to 2x minus 1 times 2x plus 9. Now I want to set my two mini equations. Either 2x minus 1 is 0. So add 1 to both sides. 2x is equal to 1, so x could be a half. Or for my other mini equation, subtract 9 from both sides. 2x is equal to -9. Then divide by 2, then divide by 2, so x could be -9 halves. So I just figured out, and I'm going to give myself a little bit more room to write my final answers here. So I just figured out that my x-intercepts were at the point 1/2, 0, because that was one of them, and the other one was at -9/2, 0. That was the other one. The comma 0, because that is by definition an x-intercept. Y should be equal to 0, and that's how I found them. For the next one, this is a case where it's going to save yourself a lot of grief if you first pull out their greatest common factor. And what is their greatest common factor? That would be 2, and in particular, this first term being negative, if you can pull out a negative as well, I would strongly recommend that, because if you can factor, it's going to make your factoring easier. So if I pull out a -2, -2x squared divided by -2 leaves me with +x squared. Positive 18x squared divided by -2 leaves me with -9x. -10 divided by -2 leaves me with +5. Then I want to ask myself, does this factor? Is there anything that multiplies to +5 and adds to -9? As far as I know, there is not. So instead, I have to break out the quadratic formula. So x is the opposite of b, plus or minus the square root of b squared, 81, minus 4a, which is 1, c, which is 5, all over 2 times a. Notice this -2 had no impact on this quadratic formula, and he'll have no impact on your x-intercepts in general. Of course, I was going on automatic pilot because I was still thinking of x-intercepts. I probably should have found the y-intercept to boost my confidence first, but that's okay. So we're really finding x-intercepts here, which meant that really we just already set this guy equal to 0. So let's make note of that. And this -2 has no impact on that because -2 does not equal 0. So let's continue simplifying quadratic formula-wise. 4 times 1 times 5 is going to give me 20. 2 times 1 gives us 2. 81 minus 20 is going to give us 61. And as far as I know, 61 doesn't really have anything that goes into it. So I think we're good simplification-wise. So we just figured out there are 2 x-intercepts. One is 9 plus the square root of 61 over 2. The other one is 9 minus the square root of 61 over 2. Now for the y-intercepts, that's going to feel like a lot less work after that process, because for the y-intercept, you plug in 0 for x, so -2 times 0 squared plus 18 times 0 minus 10. What are we just left with? -10, so the y-intercept is at 0, -10. Alright, go ahead and challenge yourself and pause this video and try to find all the intercepts of both of these functions. For this first one, let's again find the y-intercept first. So if I plug in 0 for x, that would be -4 times 0 squared minus 15 times 0 minus 9. That just leaves me with -9. So I have myself a y-intercept at 0, -9. For the x-intercept, we want to plug in 0 for x. And then I want to pull out a greatest common factor, and in particular, since everybody's negative, I'm going to make my life easier by first pulling out a -1. So that leaves us with positive 4x squared plus 15x plus 9. Then I want to ask myself, is this factorable? So is there anything that multiplies to positive 36, AC, which is 36, and adds to b, which is 15? So multiplies to positive 36, and adds to 15. So if I'm going through factors of 36, that would be like 1 and 36, which do not add to 15. I'm just having a... We also have 18 and 2, which won't add to 15. We also have 4 and 9, which won't add to 15. We have 6 and 6, which won't add to 15. 8 doesn't go in. Now we're back up to 9. So there actually isn't anything, at least that I was able to come up with. If you're able to come up with that something, kudos to you. You are officially smarter than the professor. So we instead need to use quadratic formula again. So x is the opposite of b, plus or minus the square root of b squared minus 4ac all over 2 times a. So let's continue simplifying this. These numbers have gotten big enough that I'm going to start breaking out a calculator. So we might want to figure out what 15 squared is first, which is 15 times 15. So that's 225, and then we also have a 4 times 4 times 9, which is a 144. So we have x is opposite b plus or minus the square root 225 minus 144 all over 8. Let's simplify what 225 minus 144 are. I'm feeling lazy again, so let's do 225 minus 144. That gets us 81, which is super nice. 81, square root of 81 all over 8. The square root of 81 does actually simplify, which tells me maybe this guy was factorable after all. I just wasn't thinking of it. But that's okay. So square root of 81 is 9 all over 8. Then we can go ahead and split this up into, that means there's literally two different solutions. One is -15 plus 9 over 8. The other one is -15 minus 9 over 8. -15 plus 9 gets us -6 over 8, which simplifies because both of these I can divide by 2. -6 divided by 2 gets us -3. 8 divided by 2 gets us 4. -15 minus 9 gets us -24 over 8, which simplifies to -3, since -24 divided by 8 is -3. So our two solutions are at -3, 0 and -3/4, 0. For the next one, this is an example where you definitely first want to find your y-intercept, of course, because that's usually simplest. So you do 2 times 0 squared plus 4 times 0 plus 4. Multiplying by 0 makes that go away, you're just left with 4, so we have a y-intercept at 0, 4. For the x-intercept, you plug in 0 for f of x. Then you want to pull out your greatest common factor. In this case, that would be 2. 2x squared divided by 2 leaves you with x squared. 4x divided by 2 leaves you with 2x. 4 divided by 2 leaves you with 2. Then you ask yourself, is this factorable? Is there anything that multiplies to 2 and adds to 2? In this case, there is not. So I have to use quadratic formula. So x is the opposite of b, plus or minus the square root of b squared minus 4ac all over 2 times a. So again, paying attention to what's just left in the parentheses here. So that's -2 plus or minus 4 minus 8 over 2. 4 minus 8 is a -4. So this is a case where there are no real x-intercepts. And you can really just stop there as soon as you have a negative underneath a root. So we can put all this information together in order to graph a quadratic function. So in particular, we want to really find all of our key parts, and then we want to put it all on the graph. So let's find our vertex first. So in order to find h, that's going to be -b over 2a. Negative b is a -6 becomes +6 over 2 times -1. 2 times -1 is -2, so that becomes -3. And that is the x-coordinate of our vertex. We already know there's going to be an axis of symmetry about this point, so that may be helpful to know. Then to find the y-coordinate, we're going to plug in -3 to f of x. So keep in mind that's a -1 times -3 squared, minus 6 times -3, minus 5. -1 times -3 squared is 9. -6 times -3 is +18. Drop down the minus 5. -1 times 9 is -9 plus 18 minus 5. -9 plus 18 is +9 minus 5 gets us 4. So our vertex is at -3, 4. And we're already predicting that this should be upside down because that leading coefficient is negative. Now let's find the y-intercept. So we know we have a y-intercept at f of 0. So that's -0 squared minus 6 times 0 minus 5. -0 squared is 0. -6 times 0 is 0. We're just left at -5. So we have a y-intercept at 0, -5. And we know this thing is symmetric, so there is an equidistant point over here as well. Now I want to find my x-intercepts, just so I have 2 more points hopefully to graph, and it looks like this should have x-intercepts if I was going to start connecting this. So I plug in 0 for f of x. And to make my life easier, I recommend factoring out a -1. X squared divided by -1 gives me +x squared, and all of these are negatives as well, so they factor that way as well. Now I want to ask myself what multiplies to +5 and adds to +6, and that would be 5 and 1. So x plus 5, x plus 1. Then I can set my 2 mini equations, either x plus 5 is 0 or x plus 1 is 0. The -1 has no impact on this because if you set up -1 is equal to 0, that would just be a false statement, so it makes no contribution to the x-intercepts. So x is equal to -5 if I subtract 5 from both sides, and x is equal to -1 if I subtract 1 from both sides. So I have x-intercepts at -5, 0, and -1, 0. I can attach that to our graph, and then we can connect to make our nice, beautiful parabola. The last big topic in this chapter are quadratic applications, and in particular we're usually looking at the real-world context of the vertex or sometimes the intercepts. So let's take a look at an example here, and there's a typo here that should be a negative in front of that 16. That's going to appear on your version of the slides, but just note that typo. So we have a ball is thrown upward from the top of a 40-foot high building at the speed of 80 feet per second. The ball's height above the ground can be modeled by the equation h of t is negative 16t squared plus 80t plus 40. When does the ball reach maximum height? So if we have a negative out front here, the maximum is going to occur at what type of special point? That is the vertex. So really this first question is a fancy way of asking me to find the x-coordinate of the vertex, which I can certainly do. So it would be negative b over 2a. So negative b would be negative 80 over 2 times negative 16. So that's negative 80 over negative 32. And then from here, even though I could continue to simplify that fraction, it seems like decimals would make more sense in the context of this problem. So a negative divided by a negative is a positive, and we know this will happen after 2.5 seconds. What is the maximum height of the ball? Well, to figure out what is the maximum height, that's just asking you plug this into the equation to solve for what that height would be. So you have h of 2.5 is equal to negative 16 times 2.5 squared plus 80 times 2.5 plus 40. And now that I've neatly shown my work, it's ready to plug that into a calculator, because even though I know you could do that arithmetic by hand, that's not really the focus of this class. I was trying to see if there was a way I could get this to sort of show up neatly with everybody in there. There we go. Okay. So we're going to plug in negative 16 correctly times 2.5 squared plus 80 times 2.5 plus 40. So that looks like the maximum height would be 140 feet. When does the ball hit the ground? So what that's asking us to find, if we're sort of thinking about this graph, we have height here, we have time here, and then we have a shape like this. So if we're asking when it hits the ground, what do we know is true? We know that the height has to be equal to 0 when it hits the ground. So that's what they're really asking. So that's exactly what I want to plug in here. So for part 3, they're asking for h of t to be 0. So when this whole thing is 0, it's possible that this might be something you could try to solve by hand if it just happens to be factorable, or, we could use quadratic equation. I think you've seen enough examples of quadratic equation in this video that I think it's fine if we sort of show you how you would then solve for this in a graphing calculator. So if you were going to use a graphing calculator for something like this, you would do negative 16x squared plus 80 times x plus 40, because instead of writing a t, you would want to write an x because that's what your calculator is going to understand. And then there's technically 2 x-intercepts. Which of these x-intercepts makes more sense in the context of the problem? It would be that second one, whenever time is positive. For negative time mathematically makes sense, but doesn't make sense for this problem. So that would happen at 5.458. And the units were seconds. If you weren't doing this on a part where you could just plug into a graphing calculator, certainly those results do imply we'd have to use quadratic formula. But before we use the quadratic formula, in order to make your life easier, this would be a case where you'd want to factor out a greatest common factor first, in particular negative 4, because then you would be left with negative 16t squared divided by negative 4 gives us 4t squared. 80t divided by 4 gets you minus 20t. 40t divided by 4 gets you plus 10. And, I actually could have pulled out an even bigger greatest common factor. So that actually wasn't the greatest common factor. That was just a common factor, which is cool. That happens sometimes, because I could further pull out a 2, so I'll just multiply a 2 out front there. 4t squared divided by 2 gives us 2t squared. Negative 20t squared divided by 2 gets us negative 10t. 10 divided by 2 gets you plus 5. Now you have an equation where the quadratic formula will be a heck of a lot more manageable. And then from here, that's exactly what you want to do, is you'd want to plug into the quadratic equation. You'd say x is the opposite of b, plus or minus the square root of b squared, so negative 10 squared minus 4 times a times c, all over 2 times a. And then this should simplify such that once you plug into a calculator, it becomes 5.458. But just as a pro tip, if you weren't using a graphing calculator on this part, make your life easier by pulling out a greatest common factor first. Let's look at a similar problem. So for this one, and it's not a typo this time, that's positive, this is just a cost function. First question just asks, what are the fixed costs? So what's that really asking us to find for this quadratic? Well, now we have a quadratic that looks like this. So and where x represents the number of x-ray machines, and y represents my costs. So what do I know would be true when it's a fixed cost? Well, a fixed cost is asking when you haven't made any x-rays, how much do you still have to pay? Because you still have, payroll, running the factory, etc. It's not just, the cost of the materials. So this is a fancy way of asking us to find that y-intercept. So I'm going to plug in 0 for x. Which may initially look complicated, but all these guys go to 0 and you're just left with that constant. So my fixed costs are 82,752. How many machines must be made to minimize the unit cost? Well, now the minimum cost is your vertex because we're talking about a right side up parabola. So we're still looking for the x coordinate of the vertex, so it would be opposite of b over, I should actually show the formula before I start just plugging him in. So the x coordinate of the vertex is negative b over 2a, so opposite of b is 522 over 2 times 1.2, so that would be 522 divided by 2.4. And then from here, I would definitely break out a calculator. I could do that by hand, but I don't feel like it today. Divided by 2.4, so that would be after 217.5 machines. So you should really make 217 or 218. Technically, it rounds up to 218, but probably for a real-world problem like this, they might have you round down. Or hopefully it doesn't be that borderline anyway. A slightly more interesting problem is where you have to make the quadratic equation yourself. So let's take a look at an example of that. So it says a backyard farmer wants to enclose a rectangular space for a new garden with her fenced backyard. She has purchased 80 feet of wire fencing to enclose 3 sides, as she will use a section of the backyard fence for a 4th side. So let's kind of draw this out. We have a side that's given, and then we have 3 additional feet of fencing. And she has 80 feet of wire to use. She has here the fencing perpendicular to the existing fence, so they're labeling this is L, and we'll call that a width, I suppose. It says find a formula for the area enclosed by the fence in terms of length L. Well, first of all, if I just wanted to write the area of this rectangle in terms of both W and L, that would be W times L. But I have a problem that I want the area only in terms of L. So I need to rewrite this W somehow in terms of L. Well, I have this other information about this 80 feet of wire. That 80 feet of wire is actually the perimeter, it's not the area. Area would be labeled in feet squared. So I have that a length of wire, and the width have to add up to 80 feet. So I know 2L plus W is 80. And then I can rearrange this to solve for W. So I can subtract 2L on both sides. So I know that W is equal to 80 minus 2L. And that's exactly what I can replace W with here. So I have the area, entirely written in terms of L, is 80 minus 2L, replacing W with 80 minus 2L times L. And eventually I'm going to want this as an actual quadratic, so I want to distribute the L to both of these. So the area, written in terms of L, is 80L minus 2L squared. Or to write it like quadratics I'm used to seeing, that would be negative 2L squared plus 80L. So to back up on these problems, you're given information about the perimeter. So you can write that all the sides add up to the perimeter. You know the area has to be length times width, and then you want to replace whichever variable you don't want with solving for it in the other equation. So in this case, that 80 minus 2L. Then they ask, what dimensions should she make of her garden to maximize the enclosed area? So since I have this kind of neatly written function, I just found out is the area written in terms of L is negative 2L squared plus 80L. That is an upside down parabola. So, and on that parabola, my x is considered length and my y is considered area. So if I want to maximize my area, what type of point are they asking us to find? That's the vertex. So they're asking us for the x-coordinate of the vertex to find length, and then I could plug that in to find my width. So my x-coordinate of the vertex is going to be negative b over 2a. I'm going to label what we're finding. So negative b is negative 80 over 2a is 2 times negative 2. Negative 80, 2 times negative 2 is negative 4, so 20 feet for the length. We also want the width though, so the width, well, we have an equation for that. That would be 80 minus 2L, so that's 80 minus 2 times 20. 2 times 20 is 40, so that gives us 40. So it's got to be 20 feet by 40 feet. And that would be your final answer. If they wanted to know what that maximum area is, you would just plug that back into the area equation. As always, be sure to check out your textbook for even more examples and ask your instructor if you have any questions.